Do you have part?
I still have. I do. I don't know. You know how big this is?
Okay.
Hi folks, how are you doing? So I made a bad decision of giving 3 back-to-back lectures today, and this is the third. But it's going to be a fun lecture. So today we're going to try and finish up imitation learning, and maybe touch on some policy gradient. But yeah, we'll try to get to things that are a little more practical today. Sweet. All right. So remember the structure of our class. We're still on imitation learning, step 1, right? And so we're gonna start with doing a little recap, right? We'll talk a little bit about behavior cloning, why it's maybe not a great idea, some fixes. And we introduced the idea of Dagger. That's kind of where we ended last. We'll talk about some of the challenges with Dagger and how we can do better, right? And then we'll talk about some of the modern tools that people use in imitation learning. And then we'll touch on some policy gradient. Cool. All right. So remember, we started with behavior cloning. Behavior cloning is generally the idea of you have an expert data set, some expert gave it to you, and you're trying to maximize the likelihood of A star given S star, right? You're going to treat the sequential decision-making problem as a supervised learning problem, right? And so if you have a supervised learning problem, the challenge here is that you've taken a sequential problem and treated it like a non-sequential problem. And so you have a mismatch between train and test. So train is under the expert data distribution. Test is under the policies data distribution. So you have a shift, right? So you're going to make little errors will keep getting bigger and bigger and bigger. And so essentially this is going to lead to the issues with longer horizon. So we said there was 2 issues under fitting. So we said that the complexity goes with epsilon h squared, right? And so we said that your 2 issues might be the epsilon and the h squared. So the first thing we're going to do is we're going to try and drop the epsilon. Second thing we're trying to do is going to drop the h squared. And so we started with the epsilon, and we said that, okay, like if you have underfitting, the first thing that happens is it's because it's a forward KL divergence, right? And the forward KL divergence has this issue of mode covering. So we said, okay, we're going to try and change the divergence from a forward KL divergence to a broader class of F divergences, right? And F divergence is an expectation Q, F of P over Q. For different choices of F, you will get different divergences, right? And so we said that there's the mode covering divergence, which is when you set F to X log X. There's the reverse scale, which is nicer, but you set F to minus log X, right? So now what's the issue with reverse scale? Why don't we just use reverse scale? The nice thing about reverse scale is mode seeking, not mode covering. But why is it not good enough? Yeah.
One, you have to sample from, and second, you also have to like query log plots from the expert.
That's right. That's right. So you need log plot from the expert, and you have to run the learner, right? So both of those are not great. So it's nice that it's mode seeking, but it sometimes becomes like pretty impractical for us to use in reality, right? So most people don't try to use reverse scale unless it's in this on policy distillation type approach. But the fixes here is either to change the F divergence or to use a richer distribution class, right? And so when we talk about a richer distribution class, there's lots of different options here. But the ones that we kind of talked about more explicitly were mixtures of Gaussians, latent variable models, autoregressive discretization, where you discretize one dimension at a time and stick it through something like a transformer, diffusion and flow models, and so on, right? Like, so the idea would be that mode seeking and mode covering are not issues if you're not in a Gaussian, if you have a multimodal distribution. But the trade-off here is that like it becomes computationally much more expensive and harder to train, right? With more expressive models. And you don't have things like log likelihood in certain cases, which makes like reinforcement learning and other things harder. Okay, so the second issue we said, so this is all underfitting, right? So the ways to deal with underfitting is flip the divergence or use a richer class. And those are our fixes. Now, if you want to deal with compounding error, we say, okay, we have this issue of the train and the test distributions not matching. And so the idea behind Dagger was like, let's just try to make the train distribution match the rollout distribution, right? And so we want the data distribution to match P pi theta. And so what we're going to do is we're going to start by collecting some training data from the expert. We're going to do behavior cloning. So we're going to train with behavior cloning from the human data. We're then going to run our policy in the world. When you run your policy in the world, you get a sequence of observations. You're then going to ask the human to label those sequence of observations you just visited with the true actions. You're then going to add those things back into your data set and you're going to repeat, right? So the important thing is you have to run your policy. You can't just do it offline. You have to run your policy interactively. And then you have to ask a human to label those observations with the true optimal actions, right? And so maybe like a useful way to think about this geometrically is that this is your optimal. You like made a mistake. At each of these states, you're then going to ask a human to go in and like say what they would have done, right? Yeah. Yeah. In this case, it's the same. It's not always the same. So there's an interesting class of problems where your learner, like the pi theta, is it's asymmetric. So like your learner sees a different observation than your teacher. So imagine that you had an expert which knew, like, here's an example, you're like trying to reach into your pocket to grab like your keys, right? And your learner knew your teacher knew exactly where the keys were and your learner didn't. Then you have an asymmetry problem. And so I'm not actually going to cover that here, but it's a cool problem where like your learner and your teacher are like different in observation. Okay. But it's important to remember here that like actually what Dagger says, Dagger actually doesn't literally say to do recovery. Dagger doesn't say to go back to the optimal. Dagger just says to act optimally from each of those states. And so like this picture is actually a little bit misleading. What you want to do is if your goal is here, like you would actually just like go towards the goal as quickly as possible, right? There's other methods that try to do recovery, but Dagger in its current stated form doesn't do that. Okay. Let's see. Okay, so that's all that Dagger is going to do. But the important thing is you have to run it in the world, and then you have to like ask a human to go to those states and say what they would have done at those states. Right? So at all the O's under rho pi theta or d pi theta, you have to query the expert. So that's why it's called interactive imitation learning, because it's like you have to have an expert in the loop. Okay. All right, so it works. We looked at this earlier, but that's kind of a recap, really quick. Right? Any questions on the recap? Any things that don't make sense? No? Good. All right, let's keep going. So if you look at the Dagger loop, right, there's two things that are kind of annoying. The first is that you have to run your policy. Right? Like you never want to run your policy in the world, especially if it's going to do unsafe things. It's going to go crash into the wall or something. You really don't want to run it in the world. And the second is like, if someone showed me a video of a car at different spots and asked me to label how I'd move the steering wheel, it's pretty awkward. And it's like, it's very hard to do in practice. Right? And so it's pretty hard to get humans to go back to those observations and provide action. And so the way that people have got around this is that they do this like blended control type thing where it's like the human and the robot are acting at the same time. And so you kind of mix their policies, but it's not great, right? So the two issues we're gonna try and deal with the issue of line 2, which is running things in the world, and the issue of line 3, which is asking the human to go back and label things with the optimal action. Okay, so we have step 2, which requires running policies. Step 3, which requires this like human effort post hoc, and we're going to try and address both. So let's start by thinking about can we avoid labeling things post hoc, right? So can we avoid having this loop of like running things and having humans go back to those states and give optimal actions? And so the first thing that people tried doing was they said it's pretty awkward to like look at old pictures or old images of what the robot saw and label actions. Like you'd more often like to take over, right? And so what Dagger currently does, let's say this was your optimal trajectory, right? And you like kind of messed up, and that's in black or red. And Dagger would like go to each of those states and like give you something out. And so you can kind of denote this as saying like SD comes from d pi theta. It's the distribution under your learner. And then you like label A from pi h, where pi h is the distribution of your expert, right? And so the idea of AG Dagger was that instead of like going after the fact and labeling things, what if you just allowed people to take over, right? And so the idea was that let's say there's a point after which a human is like, well, this is definitely not going right. Let me take over, right? And so then what you allow a human to do is to take multiple steps, right? And basically the human takes over the system and then drives you back to something safe, right? Or something where it like releases control again. And so the idea behind AG Dagger was that rather than going back to the states under the learner, you like essentially take over. And so there's going to be like state sampled. There's going to be state sampled from the pi theta. And then you're going to like essentially take over at some point. And then you're going to sample case steps where you're not actually acting according to the learner, but you're acting according to the human, right? So it's kind of like if you're driving, at some point you take over and then you drive back to somewhere safe. Or if it's a robot doing something wrong, you take over, you bring it back and pick something up, right? And so the more practical version of Dagger that people use in reality is like HG Dagger, and at least in robotics. But it still requires like humans in the loop and intervening and things like that. And so Pranab has been thinking about a bunch of HG Dagger stuff in the past back there, but it's harder to prove things about HG Dagger. And the reason is that like it's a little harder to prove things when you have like this mixed distribution of half coming from pi theta and then coming from pi h, as opposed to daggers all under pi theta. That makes sense? Yeah.
Use kind of like negative reward if the human has to take over.
Yeah.
Because I feel like
Yeah.
looking at the entire photo for terminal reward is kind of bad.
Yeah. So there's like this nice line of work from Sid and others, I think, where you like take the point of takeover as like you can, whenever you do a takeover or an expert stop, you can say that's like a negative one. And then you can say the point where you left off is probably pretty good. And so like you say the thing where you took over is bad, the thing where you left off is good, and you affect the Q function. Yeah.
Intervention that can also be for assuming that the human is providing expertise on that.
Can you repeat that?
Why is it here if not pi theta when the human provides that action table, which is the human intervention unit? Whereas on the normal Dagger case, when you provide basically intervention by saying it comes.
So pi theta is your learner, not your human, right? So pi theta is your learner. So what's going to happen is you're like you're going with pi theta until that point right there. And then you're letting the human take over. So the next part is from pi h. Whereas here, you never let the human take over. So you're always from pi theta. Right? And so the difference here is like this is like a mixed trajectory where you go with pi theta until you go with pi h. Whereas here, you're always from pi. Okay, so AG Dagger is cool, but it needs us to like kind of be in the loop all the time. And so what some folks at Berkeley started thinking about was, is there a way for us to change the data collection protocol a little bit to make a lot of these problems kind of go away? So there's this paper I really like. It definitely doesn't get enough attention as it should, but it's called DART. And the idea behind DART is really silly almost. It's basically like when you're collecting data, you just add a little bit of noise into your data collection, right? So it's kind of like, imagine your teleoperation interface, you're like controlling things, and like you tell it to do this, and it actually does this. You tell it to do this, it actually does this a little bit, right? So you like give it a little bit of noise, and then you force the human to correct for the noise, right? And so the idea here is that while doing data collection, you add a bit of noise into the data collection interface. And in doing so, you're like forcing the human to preemptively correct for things, right? And so there's a line of work, there's DART, there's like Tube MPC, there's Tube Imitation Learning, there's like a bunch of papers around this idea of generally trying to collect data in a tube around the optimal, where your human is constantly providing you corrected data. And so essentially you can think about it as maximum likelihood, but under some distribution where you're adding noise during data collection, right? And so one of the challenges of adding noise during data collection is you don't know how much noise is the right amount of noise to add. You add too much noise, there's nothing that can ever work. You add too little noise, it doesn't cover things, right? And so a lot of the hard parts of this paper are basically figuring out how to do the appropriate amount of noise injection during data collection to give you corrections. So they applied it to things like bed folding and stuff like that, where you have like long horizon tasks, and it works pretty well. They just add a little bit of noise during data collection. So if you're ever doing imitation learning, you have a teleop interface, add a little bit of noise to your interface, and it like tends to work a lot better. Okay, But if you're like doing heart surgery, you certainly don't want noise in your teleoperation interface. And so it's not, this is an example we have in our lab where we do things with chopsticks. And so you don't really want to inject noise everywhere. And so the next challenge that we were thinking about is how do you get this kind of corrective behavior, but without having to like have a noisy data collection procedure or human in the loop or things like that, right? And so the next question we kind of thought about, this is Abe, Yunshu, and Kay originally, and then Quinn was part of this too, is that we wanted to generate corrective data, things that help you deal with compounding error, but we want to do it without adding noise during data collection and without requiring a human in the loop, right? And so we want to say, let's operate under the same assumptions as behavior cloning or similar assumptions to behavior cloning. You just get an offline data set of states, actions, next states, but we want to generate corrective data that goes back from that gray line to that black line, right? So you want to have data that goes back, but you want to generate that without having like noise in the data collection process or anything like that. Okay, so the question that we try to ask is how do we find corrective labels, things that like help you deal with the compounding error problem without human in the loop and without online data collection, right? So it's a purely offline method. There's no human in the loop and there's no extra online data collection. So how do we correct for errors? Right? Okay, so the key idea is to like try and generate corrective data, right? So you want to generate corrective labels that bring you back to optimal. And so what we're going to do here is we're going to say, let's say you knew the model of the world. Let's say you knew how the world worked, right? So let's say you knew this function f that when taking an st and at gives you st plus 1, right? So one thing you can do is you can try and loosely set up an optimization problem that looks like this, right? And so the optimization problem says that you want to find states and actions that when played through f gives you some st plus 1 star, where st plus 1 star is a state from the expert data, right? And so you're saying that like, I want to find the states and actions which will take me back to the expert. And when I'm back to the expert, I know what to do. And so the idea is like, I can mine for states and actions that will take me back to the expert if I knew my F, right? And so if I can like, if I know my F, I can solve this optimization problem, then you can just find states and actions that bring me back in distribution, add that to my data set, and then I just do imitation learning, right? Like there's nothing online, there's nothing like that. You just mine states and actions, put it online, put it into your data set, and you just do imitation learning. The point is that instead of just having, you know, a really narrow range of things, you'll also have things that like point you back to the data, right? Etc. If you knew F. The challenge is nobody knows F, right? Like F is unknown. If we knew F, we could do lots of things. Right, so the setting we're going to consider is that we don't know F, right? But you want to use a function of how the world works to synthesize S's and A's that bring me back to optimal data. Yeah. Okay, so the thing we're going to do, as in most robot learning classes, is that we're going to just learn the F, right? And so when we say learn the F, if you take state, action, next state tuples, right? ST, AT, ST plus 1, you're going to try and learn the F with supervised learning, maximum likelihood, right? And you're going to say, like, let's say we get an F hat, right? And now you have this F hat. You can go back to your previous problem. You can say, let me find S's and A's, which under F hat bring me back to the optimal data. Right? So I want to find S's and A's, which under F hat bring me back to ST plus 1 star. Now, what's the problem with this? If I like minimize this with respect to S's and A's, what goes wrong? I just learned a model. I learned it only on the expert data, right? And now I like try to minimize this objective. Like, what's the issue? Yeah. Don't have the experts. You do have the expert state because you know the expert. Yeah, but we only had like the observed state demonstrations, but like there's dynamics, there's no guarantee that that's right. That's right. So dynamics is only good on the expert states. It could be arbitrarily bad elsewhere, right? And so one of the challenges of this objective is that it'll go and find all the holes in F hat, right? If your F hat is like bad anywhere, it'll go and find where it's bad and hallucinate things that are, falsely good. And so the issue is that F hat is only trained on expert data. It's trained on a pretty narrow range of data. So like, it's not globally accurate. So we make a small assumption here, maybe small, maybe big, I don't know. But an assumption that you're gonna like have some smoothness in your problem, right? So we're gonna say that it's gonna be Lipschitz smooth, which means that like if you change the input a little bit, the output doesn't change a lot. Right? And so you're gonna assume that the true dynamics of the world are Lipschitz smooth, and your model you're gonna enforce to be Lipschitz smooth, at least locally Lipschitz. Right? And so what that allows you to do is it says that if your model doesn't change a lot, then you can say that like you can trust your model in a small range around your expert data. And so the extra structure we're going to add is that we're going to say that your model F hat, you're going to train to be Lipschitz smooth. To do that, all you need to do is like add spectral norm regularization to your model. Yeah, that's a good question. We empirically found that it didn't work as well. But I don't know if we have a particularly deep conceptual answer. I think in many cases, like you could argue that your policy is like making bigger jumps in strategies than your model, but it's a bit problem. Good question. So you're going to enforce Lipschitz smoothness, and then you're going to like restrict your problem to only find states and actions in that gray band, right? You're not going to say find states and actions everywhere. You're only going to say find states and actions where the model is not freaking out, right? So where the Lipschitz smoothness is keeping you trusted, right? So all you're going to do is you're going to like still mine for states and actions that bring you back to optimal, but you're going to do it in like a small ball around your expert, right? But the whole point is that if you mine a small ball around your expert, and you do this at many, many different expert states, you should never deviate too far because you always have data that keeps bringing you back. So you're going to mine a corrective label, but you're going to do it close to the training data, so only where your dynamics model is not freaking out. It's a good question that Eric asked is like, if you want to do Lipschitz smoothness, why not just put on your policy? Because you could argue that like, if you deviate it far, if you deviate a little bit, if your policy is Lipschitz smooth, it also shouldn't change a lot, right? But yeah, that has to be empirically validated. Okay, so here's some examples of this in practice. And so, for all your piggy bank coin needs, this is some of our results where we saw that with corrective labels, you're able to get really precise manipulation. Whereas without the corrective labels, you see like little bits of drift, right? And so you'll see that like in precise manipulation tasks, little bits of drift lead to failed performance. Right? So significant gains in performance just from adding these corrective labels. And you can apply this to other tasks too, other precision tasks where you'll see the same type of drift in performance. So you can see the vibes are mostly right, but it's like small drifts in performance add up over time. And so, okay, so the general idea here, just to recap, is that we want to generate corrective labels, but we want to generate corrective labels in a ball which is close to the fit. And so things where your model can be trusted. Yeah.
Could you clarify quick how we get the ST and AT here? Like, are there any human labels?
No, just like run optimization pipeline.
Yeah, so we know the fine, and now we know the optional ST one.
You just like run gradient descent. So like as an ST and AT are your decision variables that you're going to do. Yeah. So you like find them enough. So in practice, often what we do is actually we set ST to ST plus epsilon, and then we find the AT that brings you back. But the point is that you synthesize ST, they're general.
Okay, and will this carry the data going to the further training?
Yeah, you just add it back to your imitation.
Adding the data.
Yeah, you just so you know dagger, but you just add it in behavior.
Okay.
And you see a big. Okay.
Real quick.
Yes.
You're saying that you're choosing like a plus epsilon so that it goes a little bit forward in the state of the expert? Is that the purpose of it?
Well, not forward so much, but like let's say this was ST plus 1. you want to choose like things in that ball so that you can find things that go back to the next one.
Got it.
Right,
And I
so-
guess, how does behavior change do that? It would just like point more directly perpendicular to the path.
Sorry, when you if you didn't do that,
Yeah, so if you're just,
if you're just searching at ST, you mean?
yeah,
Well, if you're just searching at ST, then you know the thing that takes you to ST plus 1 star is 80. So it just gives you back your training data. So like in that optimization problem, let's say you fixed ST to ST star and you just searched over 80. Right? So like what you're saying then is, let's say this was ST plus 1 star, right? And this was ST star. And if I fixed ST star here and I just searched over 80, then I would just result in this, right? Which doesn't like give you the corrective stuff you're looking for. So you want to like add a bit of noise here and go back. Good question. Yes.
So, one question, when you search for trajectories back to your expert set, what's the guarantee that it'll actually go forward rather than like to a previous part of your expert set and then just sort of like loop back?
Yeah, there's no guarantee.
Okay.
It's a good question.
So maybe this wouldn't work for like problems that have like a lot of recurrence.
Yeah, a lot of cyclic stuff. I don't think. Yeah. The other thing that's not super clear, and it would be great for someone to figure this out, is like, what you really want is you want coverage, like the data that you generate this way, you want it to like really overlap with d pi theta. Like essentially what you want to say is that like, if I'm going to start deviating with compounding error, I like want it to come back. Right? So you really want an overlap between d pi theta and like the corrected data. But it's not super obvious that those things overlap. Like the vibes are that they overlap, but we haven't proved it yet. So that would be cool to.
What if it's some sort of like exploratory policy and just like assuming you're not doing heart surgery or something,
Yeah.
just like a bunch of data without any expert intervention.
And then what would you do with that data?
And, well, you can train your model on.
Oh, on that data. Yeah. So we had a recent paper, maybe I'll cover it later in the class, but it's basically you take a bunch of suboptimal data and then you like try to use that suboptimal data to find paths back to the optimal data. And so the way we did there is use this technique called offline RL. And so you just like set all the optimal data to reward 1 and everything else to reward 0, and it tries to find the shortest path back to the optimal. So it's kind of like what you're saying. All right. Okay, so that is our challenges with Dagger, right? And so maybe let's go on to some modern takes on imitation learning. So like, I guess it's a bit of an overloaded word, right? But I think if you look at like the last 2 years of progress in robotics, at least, imitation learning works unreasonably well. It's like, I told you how it's horrible, but it's not. It like works. Like most people use this at scale and it does pretty amazing things. And so, it's worth taking a closer look at like, nobody uses like the fancy FCAN, like reverse scale FCAN technique. People still use behavior cloning, right? So, what makes it good? Okay, so if you look at like modern instantiations of behavior cloning, I think there are 2 ideas that are worth talking about. One of them is that they almost all use some version of a generative model, right? Like they don't do regression as much as they do like flow or diffusion or things like that. And the second is that they use this idea called action chunking. And so action chunking tries to predict not one step, but like k steps at a time. And so I think it's useful to like think through those 2 things, because I think like essentially a lot of the success of behavior cloning the last 2 years can be attributed to some combination of these 2 things. Okay, so they seem like kind of silly details, but I think they matter. So let's start with action chunking. And so the idea of action chunking, it seems kind of silly, but basically what it's saying is that at some time steps, at some state S, you're not just going to predict the next action A, you're going to predict a series of actions open loop from that state. Right? So when I say open loop, I'm not going to get feedback. And I'm going to say like from S, I will predict ST, I'm going to predict AT plus 1, AT plus 2, AT plus 3, till AT plus K, right? And so typically you're going to have closed loop execution. So you're going to have O1 predicts A1, A1 gets executed in the world, you go to O2, predict A2, or A2 gets executed in the world and you repeat, right? And so closed loop execution is saying every time you predict one action, you run it, you see how you do, you repeat. What action chunking is saying is that rather than just like predicting one action at a time, you're going to predict a series of actions, right? And with the series of actions, there's like different ways of running it. But often the way that you run it is you run like some number of them open loop. So you don't just run like one action, but you run A1, A2, A3, and then you do a query again, right? And so the idea of action chunking is to like change it from, one step to multi-step. Okay, and so the way that people actually do it in practice often looks like this thing on the right, which is saying that like at t equal to 0, you're going to predict 4 steps, right? And then you're going to execute the first step. And then t equal to 1, you'll predict 4 steps. And what you're going to do is you're going to take the average of the previous guess and your current prediction. And the next step, you're again going to predict 4 steps, and you're going to take the average of this, this, and this, right? And so in some ways, what you're doing is you're doing this, it's called like temporal ensembling, and you have like reducing weight into the past, right? But you're going to predict an action chunk. And it's not always that you run one step and then you recompute. You sometimes run k steps. But in general, you predict like a chunk. And then you don't just play like the chunk as is, but you average the previous chunk's prediction, right? So it's kind of like let's say I predicted these 4 steps, and here it's like this thing at this time step, I also predicted what I would have done at the next time step. So when I make the prediction at the next chunk, I'm going to average these 2, right? Or make the prediction at the next chunk, I'm going to average these 3. Make the prediction at the next chunk, I'm going to average these 3, right? And so action chunking, you predict a temporal sequence and then you average subset. Okay, so why is that good? Like, why would that help?
If we do discrete action. If we do discrete action.
You can do that with discrete action. Your averaging operation would look a little bit. Okay, so yeah, what should we like? Why is this thing good? Like, why should we ever do action chunking, right? Because we all like control theory tells us that feedback is good, right? So like, why should we do this? You're learning to predict the future, but I guess you're also learning to predict the future with like one-step actions. Yeah.
Keeps your motions smooth.
Keeps your motions smooth. Yeah, that's what good answer.
We're saying like, not just the most recent time, but like the past is at least somewhat formative.
That's right. It's similar to the smoothness. It like kind of keeps you from flipping out. You like sometimes with imitation learning, you'll have like fluctuations, but when you're temporally ensembling, you like don't jump around that much. The other thing that's useful is like part of the, while feedback is good, part of the issue with compounding error is that if I predicted something at this time step, right? Or like if I like look at the optimal thing and I like went off, like the issue is that I've like fed this thing that's slightly off into like into a policy, and like the policy freaks out if the inputs are slightly different, whereas action chunking gives us like more coherent behavior over multiple time steps, and like there's no compounding error because of like the policy input within the chunk, right? And so like if I had to keep feeding things back into the policy, you have increasing amounts of error because you fed it back into the policy, whereas in a chunk, you're just predicting an open loop sequence of actions. There's nothing going back into the policy. Okay? So it doesn't like go more and more OOD in that sense. But the trade-off here is that when you're executing a chunk, if something happens in between, you're not reactive to change, right? And so one of the challenges in action chunking is like, let's say I was like executing this chunk. Let's say I was executing this chunk, and then halfway through something happened that I didn't expect, then I need to be reactive to change my behavior. And so you kind of like, one of the open challenges here is like, you want to be able to like change your behavior reactively within a chunk. Question? No. Cool. One challenge with action chunking, and just like, really big robot policies in general, is doing it in real time, right? And so if you want to like run a robot pretty fast and smoothly, you want to do it in real time. And there's like the challenge in real-time action chunking. So here's one way to think about it. which is that imagine that you had this like obstacle and you were like trying to navigate around it. At time step 3, you're going to start doing inference, right? You have a big model, so it's going to take some time to do inference, but the world doesn't stop when you're doing inference, right? And so your inference has told you that like what it's going to give you is like this sequence, this thing that's labeled as A4, right? But the world, while you've been doing inference, has like transitioned to A10. Right? So your world has transitioned to the thing on top. So let's see. You start doing inference at this time, right? So you fed in the observation into the model. It started like predicting the chunk. But by the time the chunk is ready, I am already here, right? I'm at observation 10. And so I'm at observation 10, but my chunk has told me that I should be going down this way. But I am already on the path up this way. Now, if I like immediately take the action that the chunk told me to take, like I would jump all the way this way, right? And so if I naively just jump, it's going to lead to a huge jerk in motion. If I do temporal ensembling, it'll average this thing and this thing, and it'll go like through the middle, right? And so there's like a somewhat fundamental problem if you have like inference delays. So you typically don't think about inference delays, but with any big model, you have like lots of inference, and any fast controller, you have lots of inference delays. And so the challenge we need to deal with is like, what do I do? Basically, I'm at this step. I know that I'm going to get the inference result at A10. I know what the inference time is going to be. Like, how do I change my inference procedure so I don't have this like this jump? Right?
Maybe a naive idea might be just to alter your data such that your actions come from the future, or
Yeah, we do that. Although if there's many possible futures, you don't know which one of them you've taken.
I guess that's true.
So when we make the mistake of the trajectory, how does the loss look like? I'm trying to see how you can compute the losses here.
Which you're saying at 810 over here?
Yeah, we predict, we fail in the trajectory for predict, but how do we compute any loss there?
So we've not failed actually. We've just like basically it's not that I failed here, it's more just like this is not during training time, this is during inference time. So this is like what happens when I'm executing. So at training time, what I'm going to do is I'm going to take A3, I'm going to train on chunk, I'm going to take A4, I'm going to train on chunk. And so you have like the normal loss, right? It's more just like, and let's say it's multimodal. So there's many different paths, right? But this is during inference time. So the challenge is, what do I do during inference time that is going to this is a valid path, right? But my inference told me to go down this path instead. So how do I reconcile this path with this?
Could you just check if the states have diverged enough, then just continue on your current path and don't apply what you inferred?
But the tricky part is my current path may like end here. Right, like maybe my inference took like 7 steps and my chunks are like 10 steps. And then after 3 steps, I'm out of actions. That's a good question. So the trick that some folks at Physical Intelligence apply, which I think is kind of fun, is basically to treat it like an in-painting problem. So like are you familiar with image in painting, right? So you like hold out some frames and then you image in paint, right? Or like you hold out the left side and you in paint the right side. And so the idea here is that what you're going to do is you're going to treat it like an in-painting problem where like the left half of the image is this, right? And then you want to in-paint a set of things that are consistent with it, right? So when you start inference, you know the chunk you're going to predict, you know the chunk you're going to keep executing. And so you treat it like an in-painting problem, and then you try to like in-paint the rest of the chunk to be consistent, right? So like just because the training data never has jumps like this, you will never in-paint a chunk that is like inconsistent with what you're going to execute. And so the idea behind real-time action chunking is basically to like treat the chunk prediction problem like an in-painting problem. And so you can kind of think of it as like, I'm going to generate the remaining A11 to A15, but only conditional on the next chunk I'm going to execute, like an in-painting problem, right? So that's what helps you be like a lot. Okay, so That's action chunking, right? So we said there was two advantages or two changes. One was generative modeling. The second was action chunking. Yeah.
If you don't, if your observations from that period,
You can in-page with actions.
just actually.
You can in-page that. Yeah.
Okay.
Or you can predict observations, but I think they do in-page with percent. You are doing replanning, so you're not doing like completely open loop. You are still replanning, but you're replanning after some case steps. So you do have compounding error, but you're still allowing for feedback to, or like you have compounding error because of the environment stochasticity, not because of the policy going OOD. Right? So, but you're still doing replanning. So the hope is that you have enough coverage that if you, like, let's say you had a slightly wrong prediction, so you like went a little bit off, like you have enough coverage of your data that you could replan. Because you're still running in closed loop in every case steps. Right? Okay. All right. So action chunking. The next thing I'm going to cover is like this super recent paper. Disclaimers, I haven't read it in full detail. But I think it's a pretty cool idea. This is from some folks at CMU. And you all should go read it. It's a really nice paper. But basically what it's trying to understand is like, what is the role of generative modeling in getting like behavior cloning to be so successful, right? And so I think the high level insights from this paper, which are relevant to our discussion, is that the benefits of generative modeling don't just hold in multimodal settings. They're not just when the data is super multimodal. They also hold in data sets which are close to deterministic, which is kind of interesting. It's like, why would a generative model be useful in a deterministic environment? It's not super obvious. And then they kind of try to isolate the benefits to show that it's like from the training procedure of most flow and diffusion models, they kind of inject some type of stochasticity and they have like an iterative procedure to do inference. Whereas like a normal NLP is kind of like one shot, like you just do one shot prediction. Here you have like an iterative procedure to do inference. Okay, so let's try to understand what their claims are. And the first claim they make is that most existing data sets are not actually that multimodal. Right? And so what they did is they visualized a bunch of different data sets and they saw, like, for instance, in push key, like they're trying to push this key to this goal. It's like not that multimodal as a data set. And so, and the quantitative evidence they found is that the difference between in a generative model, let's say a diffusion model, the difference between like sampling versus setting Z to 0 versus setting just the mean Z is like not that large. And so they're saying that like it's not actually that multimodal already to start, right? So the data sets where you're seeing a big advantage in performance. And so you're seeing an advantage in performance on data sets that are not so multimodal, step one, which is kind of interesting. And then I think the step two is that they like literally used deterministic data generators. Like they did imitation learning with the deterministic policy. They imitated deterministic policy with the flow policy, and they see that like you're still seeing a 20% improvement. Right. So like that means that it's not just because of the multimodality, something else is going on that's giving you like that 20% improvement. Right. And you're controlling for model size and those other things. You're saying that like the only difference is same data set, same model size. One of them is trained with flow matching, one of them is trained with regression. Yeah. And it's a deterministic policy. So they said, okay, like this is surprising. So why do these things help? Okay, so they try to like isolate the contributions of a generative model into three parts. The first is distributional learning. Like, am I modeling a distribution over multimodal data? The second is stochasticity injection, which means that you're like adding noise to your training procedure. It's like data augmentation. And the last is that you have like an iterative procedure. Like if you think of any diffusion or flow policy, it doesn't generate an action all at once. It generates an action through iteration, right? And so they were saying like, these are the three things that are inherent to a flow policy, like which of them matter, right? And so they tried to construct experiments to isolate which ones matter. And so what they showed is that distributional learning doesn't really matter. And really what matters is injecting stochasticity and being iterative. And so what I mean by that is that they have this like, I'm going to butcher this, but they have this like interesting experiment, which they call the minimum iterative policy. And the way they do it is that they like essentially they like try to remove all of the distributionality from flow matching, and they construct this kind of weird policy. But like think of it this way. You're trying to like go from A0 to let's say A star with a deterministic policy, right? So they're going to have like, they're going to construct a policy which has two steps of denoising. In the first step, you're going to try and go from A0 to A star directly, like regression, okay? And then the second step, what you're going to do is you're going to like construct some noisy targets. And from those noisy targets, you're going to like essentially go back to A star. Right? So the way they construct those noisy targets is that they like sample Gaussian noise, they interpolate to A star, and then they take some disk along that like the flow path, right? And what they do is in the first step, they try to go directly from A0 to A star, like any regression policy. And the second step, they say that like, I'm going to go from this like noisy disk back to A star. And then at training time, I'm just going to have two steps, right? First is going straight to A star. The second is going from this noisy disk to A star. And at inference time, I'm just going to run the first step. I'm going to take my best possible guess at getting to A star. And then the second step is I'm going to like run this like essentially this denoising procedure that goes from like mistakes back to A star, right? So you can kind of think of it as like you're removing distributional. Everything is a regression policy. But what you're doing is you're adding stochasticity. So you're sampling from some noisy data and going back, right? And you're doing two rounds of computation rather than one round of computation, right? So they've constructed a simpler policy that has these like, it is deterministic, but it has stochasticity to the training process, and it has supervised iteration. Yeah, it's a little bit convoluted, but like here's the way I like to think about it is that it's kind of saying that like, let me take my best guess. Let me take my best guess at the optimal action, right? And then for the next time step, I'm going to say that if I messed up, I'm going to have something that corrects my mess up, right? So it's saying that like, I'm going to have two steps. The first step is my best guess, and the second step is a cleanup, right? And they're saying that this kind of policy is not stochastic. It is like deterministic. But the cool thing they show is that it's a little hard to see, but the MIP line, which is this like red line, is like just as good as, or not, if not better than the flow line across everything, right? So they show that the deterministic policy, just with like supervised iteration and stochasticity during training, not during test, does just as well as flow. Yeah.
Like stochasticity injection here in like generative models, sort of analogous to like, or would you think like the impact of that is like sort of similar to like Dart? Where...
It's exactly the same thing. Yeah, it's exactly the same thing, but like within the diffusion path.
Oh, okay.
So what's really cool about it is it's like Dart does it in the MDP, and this does it within the like generation path, right? So like what Dart does is basically like, this is your trajectory. You're going to add some noise. You're going to correct for it, right? Which is essentially what this figure is showing right here, right? You're going to add some noise. You're going to correct for it. And what they do is they essentially add some noise and then they correct for it, so that at test time, if you make a mistake, you know how to correct for it, right? And so they have a bunch of like nice analysis things that show that it like prevents you from like accumulating mistakes and like going off distribution and so on. But maybe the most compelling result is that they're able to match the performance of flow with the deterministic policy, which is cool. Yep.
I wonder, then, besides the thing about the auto regression policies, like, is there a takeaway here, not just about the benefit of the iteration, but like what we should be relating with it?
Yeah, I think it's like kind of an emerging theme in lots of different papers. So like, there's another paper from some Aviral and other folks at CMU where they do it for value functions. And so they train value functions with flow also, which keep self-correcting for going off. And there's a bunch of work in language models too, which are like trying to self-correct for errors. And so I think the important thing is that inject errors during training so that you can and learn how to correct for them. I think that's good insight to take away. Cool. All right. So a lot more in this paper. I only touched it a little bit, but I think it's really cool. Okay, so how is this being actualized today? The example a lot of you might have seen is from physical intelligence called Pi0. So all of those are training methods. What Pi0 and other people do is like they try to like instantiate different architectures. But essentially, if you scale up some of these ideas with great engineering, lots of data collection, and hundreds of millions of dollars, and you get like pretty cool results. And so this essentially what the results were here is that they do this. They deploy essentially a VLM with a flow matching head. So they take the embeddings from a VLM, put it into a flow matching head, and then they just train with imitation learning. They do two things which are interesting. They introduce this flow matching architecture. But the second thing they do is they do this like pre-training phase, which is like broader, worse data, but like much broader, including all of robot data from academic institutions plus their own data and so on. And then they have this like post-training step, which is just like supervised fine-tuning on like a much narrower data distribution. That seems to work as well. Okay. So is imitation learning completely solved? Yeah, it's like more solved than other things maybe, but there's still some frontiers that are interesting, right? So I think non-Markovian demonstrations are still interesting, things where you have history and you have to like account for it. Characterizing things like generalization is hard because you like kind of don't know when your model is going to generalize, when it's not. Evaluation is hard. Like we still don't have a good metric to know when it's going to work. Learning from action-free data, so things like video and those kinds of things is still hard. I don't know how to, like there's some examples where people do code training with this kind of data and it kind of works, but it's not great. Data curation is a big thing in most other domains, but in robotics, we just kind of vibe curate it. Some papers have like these examples of magic soups of data, and like it's very much an art, not a science. Dealing with things like embodiment shifts. So on the top, like you're grabbing things with a tool, and the bottom you're grabbing things with your hand. Like it's still not clear how to deal with embodiment shifts. And then designing better interfaces for faster throughput and like more high quality data generation leads to a big difference in performance for imitation learning. And so there's some good examples. This is the Umi glove where you can like, hold on to like these gloves and collect data, but I don't think it's a fully solved problem, especially for like humanoid robots and things like that. Okay, one paper I'd like to highlight from our very own student Jaffe is the idea of like doing imitation learning, but like interactive imitation learning when you have access to failures at test time. So like, let's say I like tried something, I failed. I should be able to like figure out how I failed, retry. And so we really want our policies to be able to retry in interesting ways. Some of our group thinks about this, but I don't think it's like close to being solved. And so like non-Markovian behavior that retries. Okay, I want to highlight a few other examples that I think are fun. How are we doing on time? Okay, so one example that I think is a cool technique is this idea called hindsight relabeling. Folks heard of hindsight relabeling? Some? No, not much. Okay, so let's say you have like this robot, and it's like just fucking around in this kitchen. It's trying a bunch of stuff. Some of the stuff is good, some of the stuff is bad. It's like playing around with stuff in the kitchen. And so it's like largely suboptimal data or data where someone is playing around with it, right? And so like, I guess the question is, can we make something good out of this shitty data? And so we have this like suboptimal data, we want to make good behavior out of it. And so the idea behind hindsight relabeling is that everything that is suboptimal is optimal for something. It's just not for the thing that you were supposed to be doing, right? With a loose notion of optimal. But the key idea behind hindsight relabeling is to say that I'm gonna like say that the data is not bad, it's just labeled for the wrong problem, right? So it's kind of like, imagine that I was trying to like pick something up and I picked up the wrong object. It is like optimal for picking up that wrong object, right? And so the idea behind hindsight relabeling is just to relabel, like consider not just a regular policy learning problem. Like you don't consider pi of a given s, you consider pi of a given s comma g, right? Where g is like a goal that you're trying to reach. And you're saying that like, if I had bad data, it's just that the goal was wrong, right? And so blame it on the goal. But the fundamental insight becomes that you can relabel suboptimal data to be near optimal for different goals, right? So let's say you had this suboptimal trajectory and the goal you wanted to get to was that target, G original on the bottom. instead of saying that you're going to say it's optimal for G original, you're going to say that it's optimal for G equal to ST plus H. So like when you took that action, you reached the goal, which is ST plus H, right? And so like that, it like, at least for the problem of goal reaching, it kind of got you there. Now, optimal is a little bit loosely defined because it's not the shortest path to get there. But you can show that if you like relabel things this way, like it is a valid path to get you to ST plus H. And so essentially you learn a multi-goal policy, and whenever you collect data, you just relabel the data in hindsight to say the goal at STAT is going to be ST plus H. And so you can just relabel things in hindsight, and then you get a policy that is like surprisingly good. Right? So let me see. Here's an example of a policy that is learned completely from play data, just by doing this hindsight relabeling, right? And so you can see here that like the data looks like stuff on the top, just doing random shit, right? Like stuff that is not particularly well directed. But if you relabel things after the fact, you can then command it to do specific things as shown on the bottom. Yeah.
So two questions.
Yeah.
First of all, how do you parameterize a goal?
It's a good question. If you're dealing with images, you parameterize it as like a goal image. If it's state, it's a goal state, but sometimes you do it as like a latent vector which corresponds.
Okay, is it a problem that you have a whole other parameter that you have to train over? Like it seems very.
So you're still doing imitation learning. You're not actually training, like you usually don't optimize through the goal representation. You just like train, the only thing you really do in the method is you just relabel the data. You just relabel the goal to be ST plus H, and then you just do imitation, like nothing else.
I guess my concern is that if you have a huge space of goals, then it seems like you need a lot more data to cover all of them.
Yeah. That is precluding the possibility for generalization. Like goals are related to each other. And so the hope is that you don't need to cover everything but something. But yeah, it's a valid concern that your state space is now bigger. That's why you need more data. But usually when we train it, you like collect this kind of play data. So it's like your data throughput is higher and you can just do random stuff continuously in the world. Right? So you don't have to like try something, reset it, try something, reset. Instead, you just keep collecting data.
The second question is how do you get high quality play data rather than just like.
That's a good question. So this particular paper did it, this is at Google, and so they just like paid a bunch of people to do it. We had a follow-up paper on this, which actually showed that if you like collect a small amount of data and then you just iteratively hindsight relabel things online, that it does pretty reasonably well, which is like you start by collecting some data, do hindsight relabeling, sample again, do hindsight relabeling, sample, like yourself. It like does surprisingly well. And so take it. Yeah.
Do you differentiate between the goals of not changing the environment and goals of changing the environment? Because like, yes, you can learn to play around and do nothing a lot, but to larger kind of also distribution to, oh, I dropped a box.
Right.
Now I know how to drop the box.
Yeah. So like if you, for instance, had your goal representation include the object and the arm, maybe you want to only include the object so that you only focus on things that matter, right? Like,
I guess you could, oh, here's the way. Now,
yeah, exactly.
put this from your
You wanted to preclude from dominating your data set, right? Like you might have a lot of motions in the air, but you want to preclude it from dominating your data set.
Yes, then you just filter out, like, if we go setting is only the external state, then you filter out kind of action that did nothing, basically.
Yeah. This paper didn't do that, but I think that would definitely help.
But then, don't you have a problem then, like, oh, if I have, let's say, my arm is to reach kind of pretty long to pick up something.
You might have like, yeah. I think that's totally valid, especially if you like, if you have a bunch of things of doing nothing, and then you're like, you'll have a laziness problem, basically. In this particular case, it's the play data doesn't, you cut out the pauses. So you like filter the data, so you remove the pauses. And so you at least don't have stationary data a lot. But in general, it would be a problem. I agree. And so I think the right way to do it is what you're saying, which is to focus on, maybe the more general way of doing it is focus on features that matter rather than features that don't matter in the goal report. Good question. Yeah.
I think that is to be like a automated process where it's like you have the play data and then it's like taking like somehow filter snapshots of what also you want to.
You just like take case steps in the future. And so like you don't really filter more than just taking case steps in the future. So you essentially just have a sliding window. And so for every ST80, you label the goal as case steps in the future. And so you're just saying that like, if I had wanted to reach the case steps in the future, then I would have taken this action. They're not doing stitching. They're not doing stitching. Because you're just doing supervised learning. There's no dynamic programming, so you're not doing stitching. You can do stitching by sequencing a set of goals. So like, for instance, if I like had a small set of sub goals and I like sequence the right set of sub goals, then I would get stitching. But that has to come from some other procedure. Yeah, so in this particular paper, they put the goals through some information bottleneck. They put it through an encoder with the information bottleneck, so they like alias some of the goals together. Yeah. Now here they're just doing images, but there's follow-up work that does it through natural language.
And I guess when we experiments for policy.
You could just like hindsight relabel with the VLM. I would do it. I haven't seen actually that many people who do that, but I think it would work. Yeah, go ahead.
During test time based on something that's say each steps forward.
Yeah.
And the main issue during test time, it was based on very end time step, which may not be that specific.
Yep.
For us.
Yep. Yeah, that's a good question. The question is, if you train on like a sliding window of H and then you feed in a goal that is n time steps away, which is maybe much bigger than H, is going to work. It's not going to work. So the typical strategy is either to like come up with a sequence of sub goals that gets you there, and you have like a search procedure that gives you a sequence of sub goals. Or you would like train on increasing sliding windows, increasing size of sliding windows until you get to like n. Like, so there's no magic sauce, right? Like either you have to like stay within the window and stitch the goals, or you just choose a bigger window.
Would you trainers would be able to support doing quote unquote not ultimate things like nodding over something or like taking a pause for like 10 seconds? Because it seems like you're labeling a optimal thing that would be included.
Well, I guess the question is like, what does optimal mean, right? Like in this case, optimal means goal reaching. So if the thing you want to reach is that the thing fell over, like that's the goal, right? So it's not that it's like kind of removing the notion of optimality. It's just goal reaching. So there's a bigger space of like goal conditioned policy learning, and it kind of removes the space of optimality is how quickly can I get to that goal?
So like what everyone's saying is that if like the model would always think that you're doing something useful. It wouldn't say, "Oh, I'm actually just standing here for like 5 or 10 seconds." If that's the end of a motion to pick up, say, an object, it would just say that you're picking up the object, not that you're waiting for 5 or 10 seconds.
Well, pauses are actually a problem because in a Markovian setting, pauses they keep you stuck in a loop. So you try to remove pauses, but besides pauses, yeah, you're moving towards something. Yeah. Yep. I actually don't understand. Can you elaborate? Okay, yeah. Let's chat after the class. Okay. So the second issue that I think is a big problem is that like often our policy classes are Markovian, which means that it just takes in the current state, but our demonstrators are non-Markovian, right? And so like it's tricky to say that like here's an example that I find compelling, which is that imagine you had A, B, C, D, okay? And like one of your demonstrators went this way, and another of your demonstrators went this way, and you just use a Markovian policy class, right? You just use something that takes the current Markov state. Like what's going to happen at A is that you're going to try and go to B. What's going to happen at B is you're going to try and go back to A. So you're going, right? Like, so the issue is that you had your demonstrator. Your demonstrator was a different observability and policy class than your essentially your demonstrator has a latent variable that is unobserved to the student, right? And so, especially when you have multiple people have latent variables, but you just mix up all the data and throw it into one, right? And so, one of the challenges here is that you often have non-Markovian demonstrators, but you have Markovian learners, right? And so that is going to be a problem. So humans rely on history. Mixtures of Markovian humans may not be Markovian because there's a latent variable, right? Like there's a latent variable of which demonstrator did what. If you just mix it together, it's not clear. Right? And so there's like a interesting, I won't say new, but like a line of work on like how to train non-Markovian imitation learning policies. When I say non-Markovian, I mean it doesn't just depend on ST, it depends on like a history of ST, right? ST minus one, ST minus two. And so the simplest thing to do is to just stack up all the past frames, right? So lots of people do that. They just stack up all the past frames and do imitation learning. And what's the challenge with that? Multimodal, but we know how to handle multimodal because we like have diffusion and stuff. A lot of, yeah, you need more data because your state space is exponentially larger. The other challenge here is that like, basically, if you have a larger state space, it's easier to go OOD because you can go OOD in any of those baskets, right? And so a challenge with history condition policies is the more you have frames stacked, the bigger state space becomes and the easier it is to like deviate, right?
For example, if we have two different demonstrates.
Yeah.
Why not just label the future for the demonstration as the goal?
You could, yeah. But then you need to have privileged information or like if you're just given a mixed bag of trajectories or a mixed bag of state action tuples, you know, is that realistic? No, it's not. But sometimes it's like not always super clear. Like you could have two things that reach the same goal, but in different ways. And so then it's not clear if there should be aliased or not. It's a good suggestion. The other thing that people do is that instead of just like stacking the past frames in an MLP or something, they like use a recurrent model, so like an LSTM transform or RNN, whatever. And in both of those cases, the first issue is this like the fact that it's easier to go OOD. And the second issue is like this fun paper called Causal Confusion from 8 years ago at this point. But the idea behind causal confusion is like, imagine that you were in a training setting. Imagine that you were getting a history of like your driving and you were getting a history of like previous states and actions, right? And so what'll happen is that you like every time you have like a brake light turns on, you press the brake at the next step. And so what you learn to do is you learn to over-index into the brake light. And like at test time, let's say your brake light is broken, then you like will never stop, right? And so it's easier to form these like spurious correlations. And like often because you're running things online, you'll get into states that a state distribution you might never have seen before. And then spurious correlations will completely screw you, right? And so the idea of causal confusion is that you like, with a larger set of spurious things that you could focus on, you build spurious correlations that don't hold at test time, right? And so it's a lot harder to get history condition behavior to work. Here's an example from one of my former students, Marcel, who I love to talk about. But Marcel's work came out a few months ago, but they learned to like, few weeks. But they learned to like make grilled cheeses with some robots. And they like learned to do lots of memory condition tasks. They had really cool results with largely imitation learning. And their idea was pretty simple. It was like they had two levels of memory. They had like long-term memory where they took long-term paths and converted into text. And then they had short-term memory where they had like a few video frames they put through a video encoder, right? And so the short-term memory was much shorter and the long-term memory was just like abstract text, right? And that seemed to like do pretty well. I don't think it's the end all, but I think the results are pretty cool. But lots of open questions in memory. And so, yeah, our student Pranav is thinking about this, so please bother him about it. Cool. Before we end, a few recent examples. I actually made these slides before the latest generalist model came out, but generalist has some cool examples of doing really fine sorting, and Sunday has examples of doing really fine manipulation. And the trick there is just like these sensorized gloves. They have like more and more sophisticated sensorized gloves that look like that. Right, but the point is they're light and they give you touch feedback and so on. And you can collect lots of data at high throughput. And so they just have lots of people collecting data at high throughput with these gloves. And it gives you pretty awesome fine precision results this way. So if you're interested, go check out this Gen 1 model that just came out like last week. Pretty impressive. And I put this video in just so I could put my friend Colleen on screen. I'm gonna take a picture of her. Here she goes. There you go. But basically they're like basically trying to take Gemini and make it do embodied reasoning tasks. And I think it's a little bit older at this point, but the cool thing they show as compared to most of the other models is that they're like extremely steerable. And so maybe the point I wanted to make here is that if you take really good pre-trained vision language models and you apply them with imitation learning, the models kind of tend to retain a lot of the steerability. At least the Gemini people showed so. So I think it's like a big open question in imitation learning is how to build really steerable policies. Like it's still like if you look at many of the models out there, they like will do the thing that's most obvious in the world, but they will not respond to language. And so if you're interested in like the frontiers, I would say like steerable policies is today. Okay, I think we are close to time. So maybe the last bit of perspective is that imitation learning is unreasonably effective for good reason. But it still has fundamental errors. It's not clear that it generalizes, and we're going to come up with better solutions with Dara. Cool. All right. See you all Wednesday.